So in this clip, we're going to show that over a complex vector space, invertible operators have square roots. So far the only result along these lines we've had is that if t is a positive operator, it has a square root, and in fact if it's positive, it has a unique positive square root. So now we're saying, hey, if we're allowed to use complex numbers, then any invertible operator will have a square root. All right, and so this is sort of a nice application of our theorem 8.21, our decomposition into generalized eigenspaces. So let's see, so for the proof, suppose we take the distinct eigenvalues of our operator t here, and then we'll take nj to be t minus lambda j I restricted to the jth generalized eigenspace. And then we know that nj is going to be an operator on the invariant subspace g lambda j, and we also know that it's going to be a nilpotent operator by our generalized eigendecomposition. Okay, so now we're assuming that t is invertible. So since t is invertible, no lambda j is 0, right? So t is singular if and only if one of its eigenvalues is equal to 0. That's the only way that there can be that t can have a component which is a projection, and otherwise it'll be invertible. So this means that we can rewrite t as restricted to a generalized eigenspace as being lambda j times I plus let's say 1 over lambda j times nj. So in other words, I just need to point out that lambda j wasn't 0 so that I could write this. Can't have 1 over 0. All right. So now since this part in the parentheses so actually since this part is nilpotent, 1 plus I plus 1 over lambda j nj has a square root. Let's call it qj. Then if I take rj to be the root of lambda j, and I can take that to be any square root of lambda j. So then this guy, rj, is the square root of the restriction of t to this generalized eigenspace. So now we've got it on each component, so we just have to add it back together again, or combine them. So to define R, an operator on all of V, which is a square root of T, I'm going to say, let's see, well, what does R do? Well, we first express what it does to an element of V in terms of this generalized eigenbasis. So using 8.21, I guess 821 part A, we can write V in terms of that decomposition. And then say that R applied to such a vector is how its components act on each of the components. So we do R1 on V1 and so on and so forth. Right? Okay. And then it just remains to check that R squared is equal to T. So if I apply R squared to a generic vector, then it's going to look like, since each one of these lives in, oh, I just realized I switched from U's to V's. Oops, hold on. Let me, bing, bang, fix that. Okay, so U, there we go. Okay. So since U lives in G lambda J, and G lambda J is invariant, then this guy is going to be back in G lambda J, and so I can apply it again the same way. So we end up with this, and then according to our definition of the R's, this gives us T restricted to G lambda 1 applied to U1 plus da da da. T restricted to G lambda M applied to UM. And that's the same thing as T applied to U1 up to UM, which is TV. And that was for any generic V and V. So we just showed that R squared is equal to T. So R, the R that we constructed, is an actual square root, and we are done. Now, note that the this part here, where we're checking R on the level of vectors, is we have to do it on the level of vectors because we're not in an inner product space, in which case we could take a shortcut. So if V is an inner product space, then you could define R to be R1 times the projection, orthogonal projection onto PG lambda 1 summed up to Rm times the projection onto G lambda M, and just work on the level of operators instead.